Dear students, welcome to another session of the course Analog Integrated Circuits. Myself, Assistant Professor Jasmin Sebastin from the Department of Applied Electronics and Instrumentation. In this session, we will be discussing the topics Comparator, Zero Crossing Detector and Schmitt trigger. Let us start the session. What is a comparator? As the name indicates, a comparator can be defined as a circuit which compares two signal voltages, that is, an input signal Vin and a reference voltage Vref. The input signal Vin will be applied to one terminal of the comparator and the reference voltage Vref to the other terminal of the comparator circuit. We can see the basic comparator circuit. One important thing that we need to notice is that a comparator circuit is an open loop configuration, that is, there is no feedback for the comparator circuit. Since the comparator circuit is of open loop configuration, what will be the output of the comparator? It will be either plus Vsat or minus Vsat, and this depends upon whether the voltage at the non-inverting terminal is more or less when compared to the voltage at the inverting terminal. If the voltage at the non-inverting terminal is more than that at the inverting terminal, the output of a comparator will be plus Vsat and vice versa. Let us see the transfer characteristic of an ideal comparator. What do you mean by transfer characteristic? It is a plot of input versus output. Here, by input we mean the difference between the voltages at the two terminals, that is Vin minus Vref, and we have the output Vout plotted along the y-axis. So we can see that as soon as Vin minus Vref crosses 0, the output switches from plus Vsat to minus Vsat or vice versa. This is the transfer characteristic of an ideal comparator circuit. But the transfer characteristic of a practical comparator differs slightly from that of an ideal comparator. We can see that for a practical comparator, the state of the output changes only with an increment of the input voltage by a small amount. That small amount is approximately 2 millivolt. That is, for the output to switch from minus Vsat to plus Vsat, there should be an increment of the input voltage by a small amount of approximately 2 millivolt. This region is called the region of uncertainty. And the reason for this slight increase in the input voltage is due to the presence of input offset voltage of the comparator. Now, we know that a comparator circuit has two input voltages applied to the two different terminals of the op-amp. Now, comparators can be broadly classified into inverting comparator and non-inverting comparator. For an inverting comparator, the input voltage Vin is applied to the inverting terminal of the op-amp and the reference voltage Vref is applied to the non-inverting terminal of the op-amp. The case is just the opposite for a non-inverting comparator. For a non-inverting comparator, the input voltage Vin is applied to the non-inverting terminal of the op-amp and the reference voltage Vref is applied to the inverting terminal of the op-amp. In both the cases, we need to notice that the op-amp is an open loop configuration. Let us study each of these comparators in detail. First, let us consider the inverting comparator. Here we see that the input voltage Vin is applied to the inverting terminal and the reference voltage Vref is applied to the non-inverting terminal. Let us consider the case where Vreference is a positive value. This is the input signal applied to the inverting terminal. This is the reference value which is positive, which is applied to the non-inverting terminal. So how does this comparator work? Since this is an open loop configuration, whenever the voltage at the non-inverting terminal is more than that at the inverting terminal, the output switches to plus Vsat. Let us try to identify the region. This is the region where the voltage at the non-inverting terminal is more than the voltage at the inverting terminal. This and this. So, we can see that at that particular region, the output is plus Vsat. And for this particular region, the voltage at the inverting terminal, that is V input, is more than V reference. And so the output for that particular region is minus Vsat. This is the case of an inverting comparator with a positive value of V reference. Now let us consider an inverting comparator with a negative value of V reference. See, the negative value of V reference is marked here. In this area, we can see that V input, which is applied to the inverting terminal of the op-amp, is more than Vref, and so the output would be minus Vsat. And this particular region wherein V input drops below the value of Vref, the output would switch to plus Vsat. So now we have considered the inverting comparator and two cases for the inverting comparator wherein the reference value is positive and negative. We have seen how the output varies in both the cases. Now let us see both the cases for a non-inverting comparator. This is a non-inverting comparator circuit. We can see that the input voltage is applied to the non-inverting terminal and the reference voltage is applied to the inverting terminal. Consider the case where the reference voltage is positive. So this is the region where the input voltage is greater than the reference voltage, and here the input voltage is applied to the non-inverting terminal. So for this region, the output would be plus Vsat. And for the rest of the region where reference voltage is greater than input voltage, the output would switch to minus Vsat. Now let us consider a non-inverting comparator with a negative value of V reference. For this much portion, the input voltage applied to the non-inverting terminal is more than the reference voltage. So the output is plus Vsat. And this particular region, the input voltage drops below reference voltage and the output switches to minus Vsat, as can be clearly seen from the graph. So we have understood what a comparator circuit is. We saw that since the comparator circuit is of open loop configuration, the output would be either plus Vsat or minus Vsat depending upon the difference in values of voltages at the inverting and non-inverting terminal. Now let us see the different applications of a comparator circuit. We will list down few applications of the comparator circuit. We will be discussing about one of the applications in more detail. Zero crossing detector, window detector, phase detector, pulse time modulator, and time marker generator. These are some of the applications of an op-amp comparator circuit. We will learn about zero crossing detector in detail in the further slides. What is a zero crossing detector? From the name we can understand that this particular circuit is able to detect when the input voltage crosses the 0 volt point and in which direction that is crossed. That is it increasing from positive to negative, or is it decreasing from positive to negative, or increasing from negative value to positive value. It is also called a sine to square wave converter. We will see how that is done. So a zero crossing detector is a basic comparator circuit. The only difference is that the reference voltage is 0 volt. That is, we will not be giving any voltage for reference. Again, as in the case of a basic comparator circuit, the zero crossing detector can be of inverting or non-inverting configuration. As I said, the output of a zero crossing detector shows when and in which direction the input signal crosses the 0 volt value. Let us see inverting and non-inverting zero crossing detectors in detail. First, let us see the inverting detector. Since this is an inverting zero crossing detector, the input signal is applied to the inverting terminal. We said that for a zero crossing detector, V reference is 0, so there is no V reference, and the op-amp is in open loop configuration. This is the input voltage applied to the inverting terminal. There is no V reference, or this is the V reference, 0 volt. So, whenever the input voltage is more than 0 volt, which is the reference here, the output switches to minus Vsat because the input signal is applied to the inverting terminal. And whenever the input voltage drops below 0 volt, the output switches to plus Vsat. So we can clearly see how by feeding a sine wave as input, we get a square wave as output. Let us see the case of a non-inverting zero crossing detector. Here, the input signal V in is applied to the non-inverting terminal of the op-amp, and V reference, which is 0 volt, is provided to the inverting terminal. This is the input signal, and there is no reference voltage. Whenever V input is greater than 0 volt, the output switches to plus Vsat because V input is applied to the non-inverting terminal. And whenever V input falls below 0 volt, the output switches to minus Vsat. Again, we can see how a sine wave is converted to a square wave by the non-inverting zero crossing detector. Let us move on to the third circuit, Schmitt trigger. So we know that a basic comparator as well as a zero crossing detector is of open loop configuration. So there is an issue with this open loop configuration. Even if there is a noise at the input, the output will suddenly switch from plus Vsat to minus Vsat or vice versa, which is not desirable. That is, an open loop configuration can cause false triggering of the output due to noise at the input terminals. This drawback is solved by means of a Schmitt trigger. Schmitt trigger is a comparator circuit which has a positive feedback. That is, feedback is applied from the output of the comparator circuit to the non-inverting terminal of the op-amp. Schmitt trigger is also called a regenerative comparator. And as I said, it is a comparator circuit with a feedback to the non-inverting terminal. So, why do we go for a non-inverting feedback to a non-inverting terminal? That is to solve the drawback of false triggering of the output due to noise at any one of the input terminals. We have studied many circuits with negative feedback. We studied that Schmitt trigger is a circuit with a positive feedback. Let us try to compare with the case of an inverting configuration, the difference between positive feedback and negative feedback. First, let us see an inverting configuration of an op-amp with a positive feedback. Since it is an inverting configuration, the input signal is applied to the inverting terminal and feedback is given to the non-inverting terminal. That is, this circuit has got a positive feedback. Let us see how this works. We know that the output of op-amp is Vout is equal to the gain into difference between voltages at the terminals. That is V plus minus V minus. In this case, when V input increases, it is being directly fed to the inverting terminal. So V minus increases. As per this equation for V output, when V minus increases, V output decreases. A part of V output is being fed back to the non-inverting terminal and that contributes to V plus. So when V output decreases, V plus also decreases. And again from this equation for V output, we can say that when V plus decreases, V output further decreases. That is, we can say that when V input increases, V output goes on decreasing till it reaches minus Vsat value. Let us say the case where V input decreases. Here V input decreases, so V minus decreases. When V minus decreases, from the equation for V output we can see that V output increases. V output is being fed back to V plus. So when V output increases, V plus also increases. When V plus increases, from this equation we can see that V output also increases. So when V input decreases, V output goes on increasing till it reaches plus Vsat. So this is the case of an inverting configuration with a positive feedback. From the discussion we saw that the output value would be either minus Vsat or plus Vsat. Now let us consider the same inverting configuration with a negative feedback to understand the difference between positive and negative feedback. This is an inverting configuration with a negative feedback. Input signal is applied to the inverting terminal. Feedback is also applied to the inverting terminal. The non-inverting terminal is grounded. As in the previous case, V output is equal to A into V plus minus V minus. Let us see. When V input increases, V minus increases. And as per this equation, when V minus increases, V output decreases. When V output decreases, a part is being fed back to V minus further decreases. And when V minus decreases, from this equation we can see that V output increases. So, in the case of an inverting configuration with negative feedback, we saw that when V input increases, V output first decreases, then it increases. That is, the circuit reaches a state of equilibrium. Not as in the case of a positive feedback where V output goes on increasing or it goes on decreasing till it reaches plus or minus Vsat. Let us take the next case. V input decreases, V minus also decreases, V output increases from this equation. When V output increases, V minus increases. When V minus increases, V output decreases. So, when V input decreases, first we saw that V output increases, then it decreases. That is, again, the circuit reaches a state of equilibrium. This is not the case of a circuit with positive feedback. The output goes on increasing or goes on decreasing. So, the output of a op-amp configuration with a positive feedback is either plus Vsat or minus Vsat. So, why did we discuss the difference between a positive feedback and a negative feedback? We discussed because the Schmitt trigger circuit or the regenerated comparator circuit is a comparator circuit with a positive feedback. So, from the previous discussion, I hope you understood how the output is plus or minus Vsat for an op-amp circuit with a positive feedback. Now, this is a Schmitt trigger with a positive feedback. This is an inverting Schmitt trigger. We can see that the input signal is applied to the inverting terminal of the op-amp and there is a feedback to the non-inverting terminal. So, as I said, Schmitt trigger, this is an inverting comparator. We saw from the previous slide that the output of a circuit with positive feedback is either plus Vsat or minus Vsat. And what is the value of V plus? This is a potential divider. So we can see that V plus is equal to V output into R2 by R1 plus R2. V output is either plus Vsat or minus Vsat. So we can write V plus is equal to plus or minus Vsat into R2 by R1 plus R2. This is a potential divider. Okay. This is the Schmitt trigger circuit with the input voltage applied to the inverting terminal. Let us consider the case where V output is minus Vsat. Let us assume that the current value of V output is minus Vsat. What would be V plus? V plus is minus Vsat into R2 by R1 plus R2 by this potential divider circuit. So this is the transfer chara, this is V input and this is V output. We are currently considering the case where V output is minus Vsat. Now, when will this V output switch to plus Vsat? When the value of V plus, that is the value of voltage at the non-inverting terminal, becomes more than the value of the voltage at inverting terminal. Or in other words, we can say that V output switches to plus Vsat when V input, which is the value of voltage at the inverting terminal, falls below V plus. What is V plus now? V plus is minus Vsat into R2 by R1 plus R2. So, when V input falls below this value, minus Vsat into R2 by R1 plus R2, the output will switch to plus Vsat. We saw that. Let this be that value, minus Vsat into R2 by R1 plus R2. When V input becomes minus Vsat into R2 by R1 plus R2, the output switches to plus Vsat. On further decreasing V input, the output will remain at plus Vsat. Yeah, that is what we saw. That is, initially the output was minus Vsat. We kept on decreasing V input till it reached minus Vsat into R2 by R1 plus R2. Suddenly the output switched from minus Vsat to plus Vsat. Further decreasing V input will keep the output steady at minus Vsat. Now what is the value of V output? It has switched to plus Vsat. The value of V output is plus Vsat. V output is plus Vsat and the value of V plus is plus Vsat into R2 by R1 plus R2. This is the current value of V plus. Now the output is steady at plus Vsat now. When will the output switch back to minus Vsat? When the value of V minus becomes greater than the value of V plus. The value of V plus is now plus Vsat into R2 by R1 plus R2. When V input becomes greater than this particular value, the output switches from plus Vsat back to minus Vsat. That is what we have written here. To switch the output to minus Vsat, now V input should be greater than V plus. What is the value of V plus? Plus Vsat into R2 by R1 plus R2. Once it switches to minus Vsat, on further increasing V minus, the output will remain at minus Vsat. So after reaching, we are slowly increasing V input. It reached the point plus Vsat into R2 by R1 plus R2. Suddenly the output dropped to minus Vsat because at this point the voltage at the inverting terminal is more than that at the non-inverting terminal. On further increasing V input, the output will remain at minus Vsat. So this is the path when you decrease V input and this is the path when you increase V input. I hope this transfer characteristic is clear. Okay. So this is the transfer characteristic of a Schmitt trigger circuit that we have obtained. This is called a hysteresis curve. We can see two values marked, VUT, which stands for the upper threshold voltage, and VLT, which stands for the lower threshold voltage. What is the value of upper threshold voltage? Plus Vsat into R2 by R1 plus R2. And what do you mean by the upper threshold voltage? It is that value of voltage beyond which if you increase the input signal, the output switches from plus Vsat to minus Vsat. What is the value of lower threshold voltage? It is minus Vsat into R2 by R1 plus R2. And lower threshold voltage is that value of voltage below which if you decrease V input, the output switches from minus Vsat to plus Vsat. The difference between upper threshold voltage and lower threshold voltage is called hysteresis width. And once you subtract, you can see that hysteresis width for a inverting Schmitt trigger is Vsat into 2R2 by R1 plus R2. So we saw that a Schmitt trigger is a normal comparator circuit with a positive feedback. Since the circuit has got a positive feedback, we saw that the output would either be plus Vsat or minus Vsat. Then we took the first case of an inverting Schmitt trigger, meaning the input voltage is applied to the inverting terminal, we saw at what points the output switches from plus Vsat to minus Vsat and vice versa. These points were called upper threshold voltage and lower threshold voltage. We found out the value of upper threshold and lower threshold voltage. We mentioned a term hysteresis width, which is the difference between the upper threshold voltage and lower threshold voltage. So that is about an inverting Schmitt trigger. Let us do two problems, design problems. The first question is, design an inverting Schmitt trigger with upper threshold voltage equal to 2 volt and lower threshold voltage is minus 2 volt. Let Vsat be equal to 12 volt. Here we can see that the value of upper threshold voltage and lower threshold voltage is the same. So we can directly apply the formula. When we are asked to design, it means we need to find out the value of R1 and R2. By the direct application of the formula, we can get the values of R1 and R2. Upper threshold voltage 2 is equal to plus Vsat into R2 by R1 plus R2. And lower threshold voltage minus 2 is equal to minus Vsat minus 12 into R2 by R1 plus R2. On simplification, we get 1 by 6 is equal to R2 by R1 plus R2. Let us assume R2 equal to 1 kilo ohm. We will get R1 is equal to 5 kilo ohm. And this is the circuit. Let us do another design problem. Design an inverting Schmitt trigger with VUT equal to 7 volt and VLT equal to minus 3 volt. Let Vsat be equal to 15 volt. So here one difference with from the previous question is that the value of upper threshold voltage and lower threshold voltage is not the same. It is different. Upper threshold voltage is 7 volt and lower threshold voltage is minus 3 volt. So we cannot directly apply the formula and the circuit also will slightly differ. This is the circuit. We will have to apply a reference voltage at the non-inverting terminal. So when you apply a reference voltage, the equation for V plus will change. That is, the value of V plus is contributed by V output as well as V reference. Now how do we write the equation for V plus? We have to apply the principle of superposition. First, consider V reference. When you consider V reference, V output will be grounded. Then this will act as a potential divider. The equation will be V plus or VUT, upper threshold voltage, is equal to plus Vsat into R2 by R1 plus R2. That is the contribution due to V output. And now consider V reference and V output is grounded, plus V reference into R1 divided by R1 plus R2. We need to write the equation for V plus. Since there are two voltages contributing to V plus, we need to apply the principle of superposition. We will first consider V output. When V output is considered, V reference will be grounded. And what is the contribution to V plus due to V output then? V output into R2 by R1 plus R2. That is being written as plus Vsat into R2 by R1 plus R2. Now we need to find out the contribution due to Vref. For that we ground V output. And what is the contribution to V plus due to Vref? Vref into R1 by R1 plus R2. So we can write the equation as upper threshold voltage VUT is equal to plus Vsat into R2 by R1 plus R2 plus V reference into R1 by R1 plus R2 by the application of principle of superposition and potential divider. Now we are substituting the values, that is 7 volt. 7 is equal to 15 into R2 by R1 plus R2 plus Vref. We need to find out the value of Vref also. Vref into R1 by R1 plus R2. Now what is the equation for lower threshold voltage? Same equation but plus Vsat replaced by minus Vsat. Lower threshold voltage is minus Vsat into R2 by R1 plus R2 plus V reference into R1 by R1 plus R2. Again, this is by the application of the principle of superposition and potential divider. Substituting the values, we get minus 3 equal to minus 15 into R2 by R1 plus R2 plus V reference into R1 by R1 plus R2. Now we have got two equations, 1 and 2. We need to find out the value of R1, R2 and V reference. Let us subtract equation 2 from equation 1. What do we get? 7 minus minus 3, that is 10, is equal to 15. This will be added, that is 2 into 15 into R2 by R1 plus R2. Simplifying, we get R2 by R1 plus R2 is equal to 1 by 3. Let us assume R2 equal to 1 kilo ohm. Then we will get R1 is equal to 2 kilo ohm. Now we have got R1 and R2. We know all the other values. By substituting the value of Vsat, R1 and R2 in any one of these equations, we will get V reference is equal to 3 volt. So, for designing a Schmitt trigger with different values of upper threshold and lower threshold voltage, we need to give a V reference, and this is how we write the equation for upper threshold voltage and lower threshold voltage and find out R1, R2 and V reference. So till now we discussed an inverting Schmitt trigger. We designed two Schmitt trigger circuits with same value for upper threshold and lower threshold voltage as well as different values for upper threshold and lower threshold voltage. Now we'll move on to non-inverting Schmitt trigger. This is the circuit for a non-inverting Schmitt trigger. The input voltage is applied to the non-inverting terminal. The feedback is also applied to the non-inverting terminal. The inverting terminal is grounded. As in the previous case, the output would be plus Vsat or minus Vsat. Now, here we need to find out the equation for V plus, because that would be the equation for upper threshold or lower threshold voltage. As seen in the previous problem, two voltages contribute to V plus. One is V output and the other is this V input. So we have to apply the principle of superposition. Let us first consider V input. When V input is considered, we will assume this terminal to be grounded. So then what is the contribution to V plus due to V input? V input into R1 by R1 plus R2. Now let us take V output. When V output is considered, V input will be grounded. What is the contribution to V plus due to V output? V output into R2 by R1 plus R2. We applied the principle of superposition as well as potential divider to find out this equation for V plus. Now, this is a circuit with a positive feedback. The output will be plus Vsat when the voltage at the non-inverting terminal is more than the voltage at the inverting terminal. Here the voltage at inverting terminal is 0. And the output will be minus Vsat when V plus falls below V minus. Let us consider the working. Let us assume that V output is plus Vsat, that is V plus is greater than 0. What will be the equation for V plus? V input into R1 by R1 plus R2 plus Vsat into R2 by R1 plus R2. Let this be equation 1. So as long as V plus is greater than 0, that is the voltage at the inverting terminal, the output will remain at plus Vsat. Now, how do we find the point when the output switches to minus Vsat? V plus has to become equal to 0. So for that, we are equating this equation 1 to 0. 0 is equal to V input into R1 by R1 plus R2 plus Vsat into R2 by R1 plus R2. Simplifying, we get V input is equal to minus Vsat into R2 by R1. So, for this value of V input, V plus drops to 0, and on further decreasing V input from this value, V plus keeps on decreasing. That is, it falls below the voltage at the inverting terminal. Then what happens? Since the voltage at the non-inverting terminal falls less than the voltage in the inverting terminal, the output switches to minus Vsat. This is the transfer characteristic, V input versus V output versus V input. The output is plus Vsat till the point V input is equal to minus Vsat into R2 by R1. This is the point. So at this point V plus drops to 0 and the output switches from plus Vsat to minus Vsat. On further decreasing V input, the output remains at minus Vsat because V plus keeps on decreasing. So how did we get this curve? We initially assumed that the output is plus Vsat. This is the equation for V plus then. The outputs will switch to minus Vsat only when V plus falls below 0. We equated this equation to 0 to find out the point. And we got that the point is minus Vsat into R2 by R1. This is the point where the output switches to minus Vsat because V plus drops to 0. And on further decreasing V input, the output remains at minus Vsat. So this is the output. Now, when will the output switch back to plus Vsat? When V plus becomes greater than 0. What is the value of V plus now? The output is minus Vsat. So the equation for V plus changes to V input into R1 by R1 plus R2 minus Vsat into R2 by R1 plus R2. This is the value of the voltage at the non-inverting terminal now, since the output has switched to minus Vsat. Now, on increasing V input to a point where this value becomes 0, the output switches back to plus Vsat. To find out that point, we are equating this equation of V plus to 0. And on simplifying, we get V input is equal to plus Vsat into R2 by R1. So this is the value of V input for which the output will switch back from minus Vsat to plus Vsat. See, let this be the point, plus Vsat into R2 by R1, and we are increasing V input. It has reached that value. Suddenly the output switched from minus Vsat to plus Vsat. On further increasing, output will remain at plus Vsat. Initially the output was at plus Vsat. We decreased the value of V input such that V plus the value of V plus drops to 0 and output switched from plus Vsat to minus Vsat. On further decreasing V input, the output remains at minus Vsat. Now we kept on increasing V input such that the value of V plus rises back to 0. This is the point. The output suddenly switched from minus Vsat to plus Vsat. On further increasing V input, the output remains at plus Vsat. This is the hysteresis curve for non-inverting Schmitt trigger. As in the case of inverting Schmitt trigger, we have marked 2 points, upper threshold voltage and lower threshold voltage. The value of upper threshold voltage is plus Vsat into R2 by R1 and the value of lower threshold voltage is minus Vsat into R2 by R1. And the hysteresis width is the difference between upper threshold voltage and lower threshold voltage, which is equal to 2 Vsat into R2 by R1. So with that we have come to an end of the topic comparator, zero crossing detector and Schmitt trigger. We saw 2 open loop comparators, which is a basic comparator and a zero crossing detector. Then we went for a comparator with a positive feedback, that was a Schmitt trigger. We saw inverting and non-inverting Schmitt triggers, understood the hysteresis curve, upper threshold voltage and lower threshold voltage. We worked out 2 design problems of an inverting Schmitt trigger. Thank you.